In this video, we're going to learn about U-Substitution, which is probably the most important integration rule. And the reason it's the most important integration rule is because the chain rule is probably the most important derivative rule, and U-Substitution is basically reverse chain rule. And so what we're going to be doing is we're going to be looking at integrals of functions, but it's not just going to be f of x, it's going to be f of stuff. And then what we're also going to be looking for was that chain rule part. And remember that the chain rule is like f of stuff and then stuff prime. So we're going to be looking for integrals that are in the form of f of stuff, stuff prime, and then the dx. And that way we're going to be able to integrate the bigger outside function and then just put the stuff back inside the inside function. Let's see how this makes sense in a couple of easier practice situations. Here's an integral. Could I do this normally by doing all the power rules and stuff? Yes, you could. You would have to expand everything out to the fourth and then multiply all the terms by 2x and then do it term by term. That would kind of suck. Let's do it a different way. Do I have stuff in this equation? And the answer is yes, I do. Look at this. I have x squared plus 1 to the fourth. So what I'm going to do is I'm going to say, hey, check this out. I'm going to let u equal x squared plus 1. I'm essentially making a substitution. I'm going to substitute x squared plus 1 in for u. And so my integral will become essentially u to the fourth. Except I'm not done yet because I also have to replace the 2x and the dx. Because remember that with an integral I have to have stuff with x and then the dx in order to integrate. But in this case I'm going to have stuff with u and then a du in order to integrate. So that means I need to find a du. How do I find u? Oh, well I have u, so I'm going to take the derivative. So du dx is going to equal the derivative of x squared plus 1, which is 2x. And then I'm going to solve for du by simply multiplying the dx over, so I get du equals 2x dx. Pretty easy. And check this out. Do I have a dx? Yes, it's right here. Do I have a 2x? Yes, it's right here. And so what happens is that the 2x and the dx disappear and become the du. And so my integral is simply the integral of u to the fourth du. That's it. Everything that was in the original integral was replaced with something in terms of u. And now I can integrate u to the fourth du because this is a basic integral. I add 1 to the power, u to the fifth, divide by the new power, add c, and I'm almost done. Except the thing that I need to do is substitute back the original function. And so my final answer will be x squared plus 1 to the fifth divided by 5 plus c. Check it out. Let's just take the derivative of this backwards to see that we get the original integrand. So the derivative of the constant c will go away because it's just added. And then when I do the derivative of stuff, check it out. Here's that stuff to the fifth. I'm going to bring down the 5, so I'll have 5 over 5, stuff to the fourth, and then I'm going to chain rule the stuff to the fourth. Well, the stuff inside was x squared plus 1, and the chain rule derivative was 2x. And so what will happen is the 5's will go away, and I'll end up with x squared plus 1 to the fourth times 2x. See the 2x from the chain rule? That's the 2x here that we replaced with this step of the U-substitution. And that's how U-substitution basically works. We find stuff, we find the derivative of the stuff, and we replace it. Here's another example. Do you see the stuff? I do, but that's because I'm like the calculus teacher. You'll get pretty good at seeing functions and the derivatives show up. So here, check it out. I have stuff, and a good idea is to just group a bunch of stuff together. So usually things in parentheses are good candidates for U-substitution. So we have tangent. So I'll say u equals tangent x plus 3. And then du dx is going to equal secant squared, because the derivative of tangent is secant squared. The derivative of 3 is 0, so I ignore it. Solve for the du. So du equals secant squared x dx. And now I just replace everything. So the tangent x plus 3 gets replaced with u, and the secant squared x and the dx, ta-da, get replaced by du. So I integrate u du, which is u squared over 2 plus c, basic integral, and then, I'm not done yet, I do need to substitute back the original function, and I'll get tangent x plus 3 squared over 2 plus c, and that's my answer. So once you get the hang of it, U-substitution is pretty easy. You just have to watch out for it when you're integrating. Let's take a look at a common example of U-substitution, because this is one that does happen a lot. Let's say I have x times the sine of x squared, and I'm integrating this. Notice here that that's probably going to be a good candidate for u because it's stuff. So I'll have u equals x squared, so du dx will equal 2x dx. We'll solve for the du just like we did last time, and we'll get 2x, oops, I didn't mean to write dx there. When I move the dx over, I'll get 2x dx. And now I'll substitute things, so I'll have sine of u, because x squared was u. And then I'm almost there. I have the dx here. I'll do that in red. dx. I'll have the x here. Uh-oh, I need a 2. Somebody call a doctor. A doctor counterbalance, that is. Here's how we're going to do this. We need a 2 in order to make the U-substitution work. 2 is a constant, so what I can essentially do is multiply the entire integral by 1. But I'm going to do it in the form of 2 over 2, because I need a 2. And then, because an integral is a semi-permeable membrane for constants, I can take constants in and out as I wish. I'm going to take the top 2, so I'm going to really multiply this by 1/2 on the outside and a 2 on the inside. And what that allows me to do is group the 2x and the dx together to find this du. And so when I rewrite my integral, now I can rewrite it with this du, but because I introduced this 2 and this 1/2, there will be a 1/2 continuing to stay on the outside. Now I can finally integrate this. So I'll have 1/2. The integral of sine of u is negative cosine of u plus c. And then when I rewrite this again, I'll have negative 1/2 cosine of x squared plus c. This will be my final integral. And you could double check this by taking the derivative, and you'll notice that when you get that 2x coming out, the 2 will cancel with this 1/2. That's why we had to introduce it here. I called this doctor counterbalance before because what you're essentially doing is you're doctoring up the original integrand, doctor, but then you have to counterbalance on the outside to account for the fact that you just threw a random number inside. Another important note is that you can only doctor and counterbalance with constants. And the reason you can't doctor and counterbalance with variables is because if you multiply the top and bottom by x, let's say you need it, you can't pull the x into the integral. Like, you can't do it because that's not a property of integrals. Pulling a constant inside is, but variables are not allowed. This final example will demonstrate what to do when you have limits of integration when you do a U-substitution. Now, it's important to keep in mind that whenever you have the limits will probably match whatever the original variable was. So here it was x equals 0, and we're integrating to x equals 1. So, let's do our U-substitution. The candidate will be, x squared plus 1 is a good one, so we'll do that. U is x squared plus 1, du is 2x dx. I just multiplied the dx over. We'll substitute everything. Notice that we're going to need a 2, so I'm going to doctor up and then counterbalance with a 1/2. And now I can start rewriting my integral. I'll have a 1/2 on the outside, integral. The x squared plus 1 on the inside gets replaced by u and the cubed, because it's cubed. And then the dx and the 2x for my doctoring gets replaced with du. Now I'm almost done except for these pesky little limits. These were in terms of x, but since I'm integrating with respect to u, I need to rewrite them in terms of u. How do I find u given x? Well, guess what? I have an equation right there. So I'm just going to plug in the limits. So I'll get 0 squared plus 1, which is going to be 1, and then 1 squared plus 1, which is going to be 2. And so notice that these limits are u equals 1 and u equals 2. Now I can integrate. So I will get 1/2, add 1, so u to the 4th over 4, integrating from 1 to 2, and now I have two options. The nice thing is that I can either integrate, I can either sub back the x's and do it that way, or I can just keep going, because it's area, and area doesn't change if I do a substitution. So I'll just plug the stuff in. 1/2, I'll get 2 to the 4th over 4, minus 1 to the 4th, that's a 4, over 4. These have a common denominator, 2 to the 4th is 16, 16 minus 1 is 15, so I get 15 over 8. That is my final answer, and you'll notice that if you do work the rest out here, you'll also get 15 over 8 because the integral is area, and the area doesn't change with the U-substitution. So, in conclusion, if you have limits, make sure that you change them if you're going to do a U-substitution because everything needs to match in terms of the variables. Ta-da!